Thanks. Well, welcome back, everyone. Looks like we can get started today. Well, we're in our application section, 8.3 to physics and engineering. And if you did the reading on this, I have to apologize. It's not an easy read. The second part's not so bad. When you're dealing with centers of mass, centroids, I think the author did a really great job describing how that goes together, showing relevant examples and the right formulas. The first part of those notes, though, is not, or the first part of that section, 8.3 in the reading, is really very rough. The author does a good job of describing the units, hydrostatic force, hydrostatic pressure, how to bring things together. But then the author doesn't give many examples, leaves off some formulas, and the exercises are actually really very hard on this. So I selected 3 problems specifically. 1 through 7 that look like they'd be reasonable questions that you would do on a homework and an exam. And the rest of these questions are about centers of mass and centroids. So again, the reading of the first part of that book, it's always worthwhile to read these sections before we get started, just to make your work more effective in class, work more effective in homework. But I think it takes a really, really advanced student to really understand what the author's trying to convey with hydrostatic force. So I try to fill out the notes a little bit better, but this is a pretty new topic to me. Other semesters, I just skipped hydrostatic force for that reason. But it is an important section. More and more instructors are tackling it, even though our textbook doesn't support it well. I wish they just select a different textbook. But here we are, we're going to make the best of what we can on this stuff. Any questions at all then, folks, before we get started today? Okay, well, this is how the notes start. Again, it's split into 2 different sections. Hydrostatic force will be the first topic we take a look at. And it starts off with a pretty lengthy discussion of units. Let me fix my window real quick here. So let's work through this, see what's being conveyed. And by the way, this was revised probably like 5 or 6 times this morning, try to get everything in just right, fixing units, that kind of stuff. For example, I had this in inches, seemed okay, except I didn't want to deal with this being in pounds per foot cubed and having unit conversions in the middle. We have enough going on in these notes without dealing with that. So I try to make the units as nice as possible, similar to how you're doing in the homework. So let's start off with the definitions here. This is a lot to read through, but it's good to see how it all comes together. So we're dealing with, on our first problems, something called a thin horizontal plate with area A meters squared. So that's the plate right here. We want to know what is the pressure on that plate due to the water, as well as the force, the hydrostatic force on that plate. It's submerged by depth d meters in a fluid of density rho. So that's what's being conveyed here, the depth of the water. The density rho could be in kilograms per meter cubed, and it's referred to as the mass density. So let's see if we can tie that together. Let's pick a color here. So now if we want to discuss what is the pressure on that plate due to the fluid, what we need is the volume, which is not so bad. We know the area of that plate. We know the distance. So think of a volume column of water is what the author explains on this. If we have volume equals area times the distance, then the mass altogether is going to be the density of this liquid multiplied by the volume. So it turns into density times area times the depth. So that's going to be the mass of the water above that plate. Finally, we could put this all together and say the pressure on this plate is rho times G times D. So rho, again, is the density of the fluid. D is the depth. And G right here is the acceleration due to gravity, about approximately 9.8 meters per second squared if we're near the surface of the Earth. or if we're using these units, about 32.2 feet per second squared. So that's the pressure on the plate. We take rho, the mass of the density of the water, multiply it by the acceleration due to gravity, pushing the water down on the plate, and the distance that it has to go. Any questions, folks, with that definition there? Okay, so that's the pressure on the plate. Next thing to convey is the actual force being experienced on that plate. What we take is next, force is mass times the acceleration due to gravity. The mass we found to be this quantity, rho, density of the water, area of the plate, and the depth. So the mass right here turns into this, rho, area, and depth. We throw in g right here, that's the acceleration due to gravity once again. And this can now be conveyed as the pressure times area. That's kind of nice how the units work out, but it's kind of a slog to see that. Why is it pressure? That's because pressure is rho times the depth times acceleration due to gravity. So that's rho, depth on the far right, acceleration due to gravity. Only variable left out is A for the area. So we have pressure times area for the force on that plate. In the end of the day, though, if you really think about this, the force is just going to be, if we're using, say, United States customary units, as our author calls them, just the weight of the column of fluid above that plate. So, in other words, if we're using US customary units, this is a really fast edit I threw in there. Often the delta is replaced with rho times g. Rho is the water density, g is acceleration due to gravity. In these units, it turns into 62.5 foot or pounds per foot cubed. Then delta is called the weight density of this. Other interesting units we'd want, looking at this unit discussion, is we're really just going to be dealing with the density of water and all these problems with hydrostatic force. So the mass density is 1,000 kilograms per cubic meter. So that's kind of convenient unit. And let's see, what else do we have here? Well, I think that's pretty much the major things that we want to get started on examining what is the force and pressure of the water on this plate here. Well, any questions, folks, with the write-up of these units? Okay, I'm not personally a big fan of units, so I always try to take extra time to understand them. They always get a little bit foggy and vague to me. And I think when I was reading this section, I had to reread these units several times to just see how they all interconnect. So once we have all that, here's our really quick example down below to tie these ideas together. We have a fish tank. This is pretty similar to problem number 1. We have a fish tank of 14 feet long, 6 feet wide, 10 feet tall. We want to find the hydrostatic pressure on the bottom of the tank. And we can do that right away, but let's start by just drawing out that tank. So 14 feet long, 6 feet wide, 10 feet tall. I would probably start by drawing something like this. Let's make it maybe, here's the 10 feet tall part. 6 feet wide is that horizontal segment. We also want 14 feet long. So let's draw another rectangle about the same size out here. I'm not a great artist, so this is something I practice before class just to make sure it comes out right. So going that way, that's the 14 feet. Connects going this way, and I'll do a dashed line segment here since we wouldn't be able to see that. We're imagining the whole thing is filled to the top with water. I'm not too sure how I would actually convey that. Let's just say, just for a quick note, the tank is filled to the top with water. And this is a gigantic tank, by the way. So the pressures and the force that it's being experienced by the bottom, the sides of the tank are going to be pretty severe. Let's put in the rest of the dimensions. Here's the 6 feet wide, and here's the 10 feet tall. We want hydrostatic pressure on the bottom of the tank. So that means we're calculating this right here. pressure is equal to rho, that's going to be the density of water, g, acceleration due to gravity, d is going to be the depth of the water. We have d right here, that's not so bad. So the depth is 10 feet, but notice the density of water given by our book is inconvenient for us, that's 1,000 kilograms per meter cube, but we have a unit mismatch if we're going to use that. Definitely don't want to do some crazy conversions in the middle. That's where this edit came in. The author also sneaks in on one of the paragraphs, this little statement. In US customary units, that's what we're using right here with feet, inches, and so on. Rho g we write as delta, which is 62.5. So let's write this out next as delta, that's sigma. Let me try again out of practice with delta. There's a delta times the depth, 10 feet. But for dealing with water, like in this case, delta is 62.5 pounds per cubic foot. So that's the weight density of water. So this turns into 62.5 pounds per the cubic foot is being multiplied by 10 feet. So that's a start. All we've done in that next step was taken delta, which is rho g, and plugged in that value right here. Any questions so far? Okay, well, it's a fast computation thanks to the 10 feet on there. This turns into 625 pounds per the square foot. So this is the pressure that's being exerted on water going downwards onto the bottom of the tank. So when you're designing an aquarium like this, you just have to make sure the floor can withstand the weight, because this is the pressure being observed on that bottom. Any questions, folks, with running through that computation? Okay, if we're in US customary units, the next thing we're going to do is hydrostatic force. That's this quantity up here. That's going to be pressure times area. But at the end of the day, this is just going to be the weight of the water on the tank. So this will turn into force. Sure, it's mass times gravity, but with our units, it turns into the pressure, what we just calculated, times the area of the tank. So coming down below, we'll just substitute in the value for the pressure, 625 pounds per the square foot, multiplied by the area of the tank, multiplied by the area of the bottom of the tank that we're looking for. That's a better way to say it. So the area of the bottom of the tank is 6 foot, multiplied by 14 feet. And we'll just throw all that into the calculator. Any questions at all, folks? I'm writing down the force statement, the force equation. Okay, let me grab a quick calculator here. So running through those numbers, we have 625 times 6 times 14. Whoa, sorry, those must not have been in the home row. Didn't need to pull up the console. Sorry, I had a browser issue. I'm not sure how to get out of this. Usually if you double click up here, you can move things around. There we go. So we end up with, let me double check, that was 14. 52,500 pounds. So that's the actual force being exerted on the bottom of that tank. Observe the feet squared cancel off. And so this is really a force in pounds, which is really just the weight of the water on the bottom of the tank. Well, any questions at all, folks, with those two questions there? Okay, these are like the nice questions that you'd want to start off with this discussion. And really the purpose of running through these problems right here is, it's more about, let me fix my window again, more about just getting used to the units, the force equation and the pressure equation. But the bigger question we might want to ask is not necessarily the force on the bottom of the tank. Again, that's just the weight of the water. That's pretty fast to calculate. What's really curious is, what is the force on one side of the tank? Say the front face, for example. That's interesting. because now we have a little bit of drama on this kind of problem. The trouble is the lower you go in depth, the more weight of the water is being exerted against the wall. So the force on the wall depends on depth. It changes with depth. And we want to know the total force on one side of that wall right there, not completely straightforward to calculate. So that's the next thing we're going to look into. Any questions whatsoever at this stage? Okay, this is all one problem in the homework, but I felt like for the notes, it was great to break it up into just two problems. Here, we're just looking at the units, investigating the pressure equation, the force equation. But on this one, we want to find hydrostatic force on one end of the tank. So let's put that there just as a temporary screenshot. When it says on one end of the tank, answers could vary on these kinds of things. The back of the book is usually talking about the face that has smaller area. So I'll usually go with that approach. So when it says find the hydrostatic force on one end of the tank, I'd be thinking this end. But again, there's multiple correct answers if you're thinking the other longer end of the tank as well. So focusing on that end, what we want is a front view on here. So here's the front view. So it's 10 feet tall, 6 feet wide, so that should do the job. 10 feet going this way, 6 feet going this way. I think we're done with this as a screenshot now. So this is the front view where it's shaded right here. Oh, that didn't completely delete, I guess. Again, the water level is right up here. It's a little bit easier to convey now that it's a two-dimensional drawing. Let's call this the water level. We're assuming here it's filled to the top, which is concerning. You wouldn't want a magnitude earthquake even, your fish could fall out. But let's assume it's filled right to the top, maybe even a meniscus on there that you could see. So if that's the case, here's where it gets a little bit weird. We need to put in an axis. So here it is. Let me try again. That'll do the job. And on our axis, it's convenient to take the level of the water as the zero. Then going down, we're really interested in the depth. So we want to have going down be the positive direction. What happens next is we want to put in as much information as possible on the scale. So at 0, that's the water line. Go down to this value, that's 10 feet down, but in the positive direction, we'll call this positive 10. And that's our drawing so far. But again, we have a lot of drama on this kind of problem. The pressure on this point right here is not the pressure down here, the same as the pressure down here. The weight of the water causes more pressure on that region versus on this region of the face. So we need to convey that when we go to find the total hydrostatic force on this end. Now, how in the world will we do that? There are formulas here, so that's always very helpful. Our author does not provide any formulas whatsoever in the reading, so let's do it his way first, then we'll show how to do it using formulas on the next problems. The very first thing we have to do is take this interval from 0 to 10 and partition it into n subintervals of equal width delta x. Essentially what we're going for is a Riemann sum. So let's say delta x is going to be 10 minus 0 divided by n. So 10 is the lower limit of integration eventually. 0 is the upper limit of integration. We are breaking this into n subregions. So let's write this out as x naught is this one. X naught will be here. X1 will be here. X2, X3, and 10 will be X4. So in my diagram, this is for when n equals 4. Now, what can we do next? Well, the moment we found all these values, we can come over here and start breaking up the front of the face. So we could call this, as our author does, the first strip. Strip 1. The second strip goes from X1 to X2 on the scale, so strip 2. and so on. Here's strip 3 and strip 4. So now we have 4 different regions. We've got the same problem with the entire front face, where if I'm on strip 1, where the red dot is, the pressure on the wall is different from when I get a little bit lower. But this is actually okay because we're imagining n is going to get really large. When n gets really large, these strips get really, really thin, and the difference in pressure from the top to the bottom of those strips becomes extremely negligible. So that's what we're going to take advantage of. We need a sample point somewhere between these. Well, let's start by saying the pressure on the ith strip is Pi. Well, we need to recall our pressure formula. Pressure at the ith strip will involve rho, mass density of water, g, the acceleration due to gravity, times a distance is what should go here. Or instead of saying distance, let's say depth of the water. Looking back at what we did prior, let's take a look just for a quick look to see if we're on the right track. Rho g times depth. That's what we're doing in this nice situation right here. We're looking at the pressure on the bottom of the tank, no issues. We just take pressure times depth. That was this total segment right here, and it was 10 feet in this problem. But here we have to use a little bit more ingenuity. When we say ith strip, we're saying I between 1 and 4, and eventually that's going to become a large number. But we can take a generic sample point. Let's call it, say, xi star. So if this is the ith strip we're describing, xi star is going to be the depth at this value. Not exactly because, well, the depth goes between x2 and x3. But again, as n gets larger and larger, that becomes the accurate depth as the width of those strips becomes smaller and smaller until that's about the right value to put in. So we'll put in that this is approximately, admitting it is approximation at this stage, xi star. So that's going to be the pressure at the ith strip, approximately right around here, for example, if we're thinking strip 3. Any questions so far, folks? Okay, the only difference from example 1, part A, is instead of putting a distance d, we just put in a generic value, xi for the depth of the water. That's again the reason why we have an axis going this way, which looks kind of odd. But the top of the water as a fill line is a great place to start your axis at 0. Well, next thing we want is the actual force. So let's say the hydrostatic force on the ith strip is, well, recall for the force equation, you just take pressure times area. So that's not too bad to deal with. So force on the ith strip, I'll call it Fi, is the pressure on the ith strip multiplying by the area of ith strip. But the area of all these strips are going to be the same. They have the same height, delta x, and the same width, 6 feet. They get a little bit trickier if, say, for example, this is a rectangle. If it's a different shape, we have to work a little bit harder, but not so bad to specify on this one. We can say that this is the ith pressure, it's rho g times xi star, multiplied by the area of the ith strip. We just take delta x, multiplied by the 6 feet. So let's put that in as, let's go 6 feet first, times delta x. So that's going to be the force approximately on this strip right here, the ith strip, which could be any one of these 4. Any questions at all, folks, to that step? Okay, Now, even though it's a pretty blunt approximation, we now have at least an approximation for the hydrostatic force on this front end of the fish tank. We can say that the force, let's say in the notes, the total force is just F for the force altogether. It's going to be the summation of all of these partial forces that we found on each one of the strips. So it'll be a summation as I goes from 1 to n. Again, in our problem, it's from 1 to 4 with what's given on this diagram. So summation as I goes from 1 to n generically of this thing, this force, Fi. Let's just write that in to connect the dots, which is going to be equal to summation as I goes from 1 to n, rho times g times xi star times 6 delta x. Let's see if we can make that a more convincing star. Okay, so to reconvene, let's just summarize what we've done so far. Finding the hydrostatic force on the total front face is difficult because it changes with depth. So we just looked at small strips independently. We found the pressure of one strip, the force on one strip, and now at this stage, we're just adding them all together. It's, again, a very blunt approximation. I should emphasize that right here. The force is approximately equal to this quantity right here. The only way to make this a better and better approximation is n has to get larger and larger. That way, everything here that's been approximated gets better. And we can say finally, the force is exactly the following. F equals, well, it's this approximately. So if we said say dead on equals, we're doing a limit of this as n goes to infinity. So limit n goes to infinity. Imagine what we're saying here is that this is not 4 strips. Imagine the picture if it was 40, 400, 4,000, and so on, just getting larger and larger. So if we're doing that, we have the limit as n goes to infinity of the summation as I goes from 1 to n of this entire quantity, rho times g times xi star times 6 delta x. Now, doing that limit does not look reasonable or fun in any kind of way. These are often really awful limits. But let's say here, the big takeaway, this is a limit of a Riemann sum. That deserves 2 exclamation marks, even though, let's do 3, why not? Even though in English, you're only supposed to use 1 or none. This is always really special because if you can write down a problem as a limit of Riemann sums, like we did in section 8.1, it means you're really dealing with a definite integral. So in that definite integral, rho and g are constants, so we can put those outside. I want to leave the 6 there. We'll explain why in a moment. Where are we integrating from? It's going to be from 0 to 10 using this axis. That's where the partition came from on the Riemann sum. So integrate from a lower limit of 0 to an upper limit of 10. And what's else? The xi star turns into just x. 6, I still want to leave in that position. Again, we'll explain why soon. And the delta x, that just turns into dx. So now that we see this so far, let's mention what the shortcut is. When you're doing this in the homework, you don't have to do the Riemann sum, but if you did the reading, that's the only way the author presents how to do these problems. But we can make an observation right here. There's an actual formula. The author just didn't give it to us for some reason. Let's take a look at the diagram and connect the dots. So this will just be a temporary screenshot. So when we did this, we're always going to have rho times g right in front of the integral. So that's a given in the problem. Only differences are whether we're using ordinary units or US customary units. But notice that that 6 is special. The moment you pick a value of x anywhere on here, it produces a line segment that goes this way. Maybe we'll leave this as the screenshot just in this position. That we like to call L of x. And so this is the length at x, or L of x. This problem wasn't so bad because wherever x is, the length is always 6 feet because we're dealing with a rectangle. We'll see how it conveys in a Harvard problem in this one. Then the value for x here, this is always going to be the depth below the surface. So these always come together in that kind of way. So if we didn't do any derivation with this Riemann sum, we still would have said the hydrostatic force on the front view of the tank will be the mass density, acceleration due to gravity, integrate from depth of 0 down to a depth of 10, so 0 to 10. X is just going to be the depth that we're dealing with. In all my problems I'm asking, it's pretty much just going to be x here. The hard thing, not in this problem, but in other problems, is you also have to put in the length of the strip, or the length of this plate here at the height x. Just happened to be 6 on this one. Well, finally putting all that together, let's finish off this integral and show what the formula is. Yeah, go ahead.
Where do we get delta x?
The delta, oh, this right here?
Yeah.
That's a good question. It's a little trick with the Riemann sum. Let me see if I can pull that up again. Here we go. So whenever we have a limit of Riemann sums like this, the cool thing about it is your xi just turns into an x. And the delta x just gets conveyed as a dx for the notation integral. So that's why we're happy in our section 8.1 of producing that delta x in our derivation. And finding the delta x right here, there we go, just tells us we're on the right track again. It just gets full on replaced with dx. Other questions about that? Okay, thanks for asking about that. In a real sense, like we mentioned before, applications to the integral are almost always doing something like this, taking a Riemann sum and writing down the integral. Maybe that's why the author didn't give the formulas, but really if you're treating the subject of hydrostatic force with a little bit more dignity and honesty, those are formulas that you ought to give, I'd say. And so pretty much everyone who teaches Calc 2 and this topic would give that formula we're describing, even though the book doesn't. Other questions at the moment? Okay, well, let's finish this off. First thing we want to do is take a look at the units we're dealing with. Rho g depends on units. And here we're dealing with feet. So scrolling up to the notes, rho g becomes delta, if you prefer to write it in delta. But at the end of the day, if we're dealing with water, it's 62.5 pounds per foot cubed. So that's what rho g is going to turn into. So here's our first substitution. Rho g right here becomes equal to 62.5. I actually think the better number is 62.4. I've seen that in other books, but our author uses 62.5, probably just because it's a round number. Kind of a curious choice. Then we're integrating from 0 to 6 of 6x dx. Kind of a relaxing integral once we get to this stage. The hard part is knowing what the form of the integral was in the very first place. But continuing on. Oh, that was a mistake. Thanks for spotting that. It looks like a copy error. Must have been eyeballing the 6, not the upper limit there. So yeah, good catch on that one. That should have been an upper limit of 10. Other questions so far? Okay, with that better value put in, let me just double check. Yeah, should have went down to 10. We now have 62.5 times 6. Let's throw that in. That comes out as a 375. Next, take the antiderivative of x. So that's going to be times x squared over 2. I'll put the division by 2 under the 375. Evaluate from 0 to 6. That's a fast evaluation too. This turns into 300. Oh geez, that is supposed to be a 10. Thanks for spotting that one again. Must really like the number 6. 0 to 10. Thanks for spotting those. Then 375 divided by 2 times 10 squared minus 0. So just 10 squared. Let's go back to the calculator. Here's the 375. Let's just type it in so it looks more convincing. 375 times 2, or excuse me, divided by 2 times 100 gives us 18,750 pounds. So that's the total force on the front face of that tank. So if you're building that from scratch, your construction has to account for this being the maximum amount, if it's filled to the very top, for a hydrostatic force on the front. That way, if you account for that, it won't just completely collapse. So a lot goes into that kind of problem. Any questions at all running through this one? Yeah.
That's the total pressure across the entire front of the face, right? Not just volume.
The entire front of the face, exactly. So again, that was a tough problem when you think about it because the pressure changes as you go, but now we're coming up with that total pressure now at that stage. Other questions at the moment? Okay, so just to take a look at it again, let me hide that definition onto the next page. If this is all you saw, let me also convey, this was a screenshot, so we probably don't want, let's just use this pen right here. Oh, that's too much. Okay, let's redact this and this. That's just an artifact from taking a blunt screenshot. So if you were doing it from scratch, just based off this, imagine those vertical strips are gone. You would have said that the force is equal to rho times g, integrate from 0 to 10. Try to get that number in. There we go. Then you put in an arbitrary x. That's going to be the depth. X is between 0 and 10. Multiply by the width at x. It was always 6, so we throw in 6. And integrate in that format. It just takes a long while doing it with the Riemann sum. I mean, it's good to see once because your problems could be something totally different from this in some other applied setting, but Riemann sum can still sneak its way in. With the Riemann sum, it's a lot of work, but the way we're doing it in class, this is a totally fine solution. You can use the formulas that we're about to describe. Any questions to this stage? Okay, so either way we look at it, a limit of Riemann sum, or just jump directly into the definite integral, that's the total amount of force being experienced by the front of the fish tank, 18,750 pounds. Not as much as the force on the bottom of the tank. That one was 52,500 pounds, because that's the total weight of the water acting on the bottom. This weight on the front of the plate, again, we're adding up total amount of force, where the force is low here, and it just gets higher and higher and higher. Through integration, that becomes the total force. So here is the generic situation after looking at through all of that. Generically, we're looking at just a thin vertical plate. So we want to know what is the hydrostatic force on this plate right here. It could be a certain amount of depth below, or the plate could be right at the water line. Just depends on the problem. In either case, the force exerted on the force from fluid exerted on this side of the plate is going to be done in this way. You take rho times g, that's the weight density like we said before. You integrate from A, that's where the object starts, down to B, that's where the object ends. You take X, X is the depth of the fluid. So imagine putting down your X right here, for example. There's your depth going from A to B. L of X, this is the not so easy thing to find, is going to be the horizontal length of the plate at X. So once you put down X, you need to come up with a formula for this. L of X. With the shape that I described, that looks like it could be a pretty nasty thing to do. And it's kind of curious in the homework problems. I was trying to do some to decide which ones are great to do in class or to assign in class. It says here, we're doing 1-3. I tried for problem 5, right next to problem 3, but the complexity from problem 3 to 5 is astounding. You go from something that's a triangle to something that's a circle, but the one with the circle involves all sorts of ideas. It involves a trigonometric substitution, trigonometric integrals. It looked like it'd be something that takes like 30 minutes in class for real for us to get through. So I won't be assigning those in class. Think of what we're doing here as a very basic introduction to hydrostatic force. That's pretty much all our author provided as well. So the questions that you might see in homework and on exams are similar to example 2 and the example 3 we see down below. Well, that's our formula. Here's the schematic that shows how it all goes together. Any questions with that integral formula down below? Okay, well, let's take a look. Here we're dealing with meters, so let's first deal with units on this. If our unit is meters instead of feet, then rho times g is going to turn into, let's see, first it was 1,000 for the density, rho, then 9.8 meters per second squared for the acceleration due to gravity. So this just turns into 9,800. So that's rho g in this problem if you're dealing with meters. Let's say that. For meters, it's kind of nice that this part of the problem is totally decided, only because we're dealing with the weight density of water. I'm not going to give anything like kerosene or something like that. So for meters, that's our rho g. The next thing we have to work on is, well, to get x and L of x, we do want an axis on this. So here's our vertical axis. Right at the water line, you think of that as a distance 0 below the water line. We're going as low as a distance of 11 meters. Next, we just pick a value of x. That's going to be the depth of the fluid. It could be anything between 0 and 11, but usually you'd want to put it somewhere over here just to make a pretty diagram, and we go to write this out. The moment you've nailed down x on your diagram, you can come over here and put in a horizontal line segment. There to there is L of x. So we need a formula for L of x. Anyone happen to know the trick to get the formula for that quantity? If someone came up to me in the street and said, solve for that L of x, you know, in all honesty, I think I'd draw a blank. I would have to have a lot less pressure put on me and time to think about it. And this is how it would really go down. We can solve L of x using similar triangles. So that weird concept you probably saw it potentially in high school algebra, high school geometry, keeps coming back and back. It's been used in our textbook in Calculus 1 in different settings here and there. Comes back in full force for this kind of problem as well. So similar triangles means we're thinking of one triangle, the big one in black. It is proportional to the little triangle where we have L of x as the base. So let's put down that little triangle. The base length is L of x. The height of it, well, that's just the height of, well, the distance below the water line, x. So we'll say going this way is x, the height. And now in forming similar triangles, you want to take corresponding lengths in this kind of way and form a proportion. So in other words, the proportion of the base, 7, to the height, 11, these are in meters, but they cancel out in units, is proportional to, we need to do this in the same order. So we put the base in the numerator coming from here. We need to take this base and put it in the numerator for our next proportion, L of x, divided by the height again, x. So looking at the color coding, I think let's keep that color coding going. This is 7 and L of x, those are the two bases. 11 and x, those are the two heights. Well, that's a similar triangle setup, and they're fast to solve. Just imagine multiplying both sides by x. You would then get L of x equals 7/11 of x. So that's going to be the description of what's going on here. Notice the 7 and 11, if you did this like 100 different times, you're just going to drop it back down here to get your answer out. But it's good to see how this process works, because if you do similar triangles in a different context, your triangle might be a different type, maybe a right triangle, something different. Well, any questions, folks, to this stage? Okay, well, it looks like we have all of our components. We have rho g, 9,800. X is just x, the depth of the fluid, or the depth below the water line. We just found L of x, that's where most of the fighting is. Let's put this on a new page and then finish it off. So all this work assembles to say the force on one end of this plate due to the hydrostatic pressure is going to be F equals rho g, integrate from 0 to 11. I always want to put these in the opposite order, but keep in mind your axis is going in the opposite direction. Positive is down. So you flip those limits of integration going back to the integral. Then it's going to be x multiplied by 7/11 of x dx. And again, when you do the reading on these problems, our author does not use that formula. He does another Riemann sum approach. And you still have to do similar triangles on that. But again, at the end of the day, if you're doing hydrostatic force a lot, you're probably not using a Riemann sum on every single one of those problems. You would do it for the oddball cases. But this one's a pretty more straightforward kind of problem. We get down to here, and now we're ready to just start integrating. Any questions, folks, to this step? Okay, well, continuing on, let's see what we can do with this. First, for rho g, here's the 9,800. We can pull out the 7/11 outside of the integral. So there it goes. Then we're integrating from 0 to 11 of x squared dx. Usually the stage of the process goes a little bit faster. There's nothing too crazy going on, except that 2 looks hard to read. So I'll just leave my numbers in a factored form so far. 9,800 times 7 over 11. Antiderivative of x squared becomes x cubed, and I'll divide by 3 down here in the denominator. X cubed will be evaluated from 0 to 11. So this turns into 9,800 times 7, divide by 33. Then we put in 11 cubed minus 0 cubed. And we're ready for a number right at this stage. Any questions, folks, to that step? Okay, now it's calculator time, so let's make this calculator work for us. 9,800 times 7, divide by 33, multiplied by 11 cubed, gives us this neat figure. Let's see, 1, 2, 3, 4, 5, 6, 7. Let's call this 2.77 times 10 to the power of, let me double check my decimals, 1, 2, 3, 4, 5, 6. 10 to the power 6, rather. I was thinking 10 to the power 7. That's not with scientific notation. Does that look better, folks? 10 to the power 6? Awesome. And this has a unit. Because we're using the metric system, this would be a unit of newtons for the total force. So 2.77 times 10 to the power 6 newtons. Quite a large number, but this is a pretty big structure as well. 7 meters that way, 11 meters tall. Well, we did it, folks. That's dealing with hydrostatic force. And again, I feel kind of guilty that our math department has made our textbook mandatory for every calculus class, because this one section deserves kind of a better coverage, but the reading is really rough. I think it takes a pretty advanced student to actually read that, and only that in the textbook, and then solve those three questions right there, 1 through 7, without any extra support. I think that's a tough set of problems. So when you're doing this in the homework, take advantage of this formula right here and makes the life a lot easier. You don't have to do it the author's way of doing the Riemann sums. And because the presentation of this portion of section 8.3 isn't the best, when it comes to exam questions, it's going to be extremely similar to either example 2 or example 3. I'm not going to put anything too wild there. Example 2, example 3 are also highly similar to what you're doing in the homework. So if you can get through the homework problems, you're essentially doing the exam question for this subsection. Well, that's our discussion on hydrostatic force. In a real engineering class, there is so much more to say here, but it's tough to do it as an application in calculus because there's limited time to discuss all the related topics around it. Next, we're going to turn into centers of mass. Our author, as opposed to this subsection, does a really great job on the write-up on the centers of mass, the derivations, and providing all the formulas. So that section will take a little bit more time on. Well, the time we have, looks like we've got about 17 minutes. We'll probably come back and finish this next class. We may take a little bit longer and finish on Monday if necessary. So here's our next set of discussions. Looks like a wall of text, so let's put in a little bit of space here. So let's focus on this end of the notes for the moment. Sorry, I should have put in the space when I put it in the notes originally. So when it comes to centers of mass, what we'd like to start by using is the so-called law of the lever. Here's how it goes. We'll have two masses, mass 1, mass 2, think of them in grams or kilograms. They're attached to a rod of negligible mass on the opposite sides of a fulcrum at distances d1 and d2. So let's start by drawing this out. Here's mass 1. Here's mass 2. This is a rigid system where the masses are connected by a rod of negligible weight. Think in terms of like a really massive dumbbell or something silly like that, where the actual handle part, that's negligible, almost no contribution to the system. It's M1 and M2 that have the most impact on the system, but it's just rigidly attached by some kind of beam like that. We're imagining, where would it balance? Imagine a teeter-totter, that's the fulcrum. If I put the fulcrum here, then I'm emphasizing that right at this point, the whole system is going to balance. It kind of implies that mass 2 is really massive relative to mass 1. And the only reason it's balancing is because of leverage with mass 1. So in this picture, although it's not necessary for the derivation, mass 2 would certainly be bigger than mass 1. Think of, say, a grown man on a teeter-totter with an extra long segment for a small child. So that's a setup so far. Next thing we have to put in are the distances. We have distances d1 and d2, and that's the distance from here to here. d1, that's the distance from here to here, d2. So the law of the lever is that this rod balances across the fulcrum if the mass 1 times the distance 1 is equal to mass 2 times distance 2. Kind of a curious statement, but it's something you could verify with a really quick physics experiment. And so we'll take advantage of that and consider it to be a true law. Any questions at the moment, folks? Okay, so let's bring this up here. It says next, now suppose that the rod lies along the x-axis. Let's maybe do a new diagram here to show what's going on with that formula. Lies along the x-axis with masses m1 at x1, mass 2 at x2. So only difference now is we're going from the law of the lever and imposing an axis. Definitely we're looking at math now. So here's our axis going this way. Here's mass 1 like before, located at x1 on the number line. Mass 2, located at x2 on the number line. Let's say the fulcrum is still at this relative position. What is that point here? That's going to be x bar. Deserves a new color. The point where it bounces is x bar, and that's provided through this formula. So our goal is to say, What in the world is going on with that formula? How can we explain how the law of the lever, that's this equation, turns into that thing? It seems like it's almost a pretty far leap. But here's how it goes. What we need to convey is those actual distances. So the distance from here to here would be x bar minus x1. Distance from here to here, let's use the arrow strategy, would be x2 minus x bar. So we do in fact have distances. If we reuse the law of the lever, we would take mass 1 multiplied by distance 1. Distance 1 is x bar 1 minus x1. Set that equal to, now we're on this end of the law of lever, take mass 2, multiply that by distance 2, that's this distance, x2 minus x bar. And our goal now is to solve that equation right here for x bar. My claim is we should get that. So let's see, excuse me, if the algebra is really working. The math is really mathing so far. So first thing we want to do in solving for x bar is distributions. So this will be mass 1 times x bar minus mass 1 times x1. Another set of distributions is mass 2 times x2 minus mass 2 times x bar. Next, bring your x bar terms to one side, all other terms on the opposite side. So that term is frozen here. Mass 1 times x bar. Add mass 2 times x bar. Add to both sides of the equation, mass 1 times x1. Mass 2 times x2 stays right exactly where it's at. Finally, you can factor out x bar from this. X bar would multiply mass 1 plus mass 2 equal to mass 1 times x1 plus mass 2 times x2. Finally, divide. X bar is going to be equal to mass 1 times x1 plus mass 2 times x2. Divide by the total mass of the system, mass 1 plus mass 2. Double checking. Yeah, that's the same formula that we got here. So this is essentially just the law of the lever with an x-axis thrown in, using these quantities, x bar, to describe the location of the fulcrum. Let's, oh, there we go. Sorry, Microsoft is always actually a little bit funny towards the end part of class. I think it just gets tired. So that's how x bar gets calculated. So that's the exact position where we have a center of mass in a one-dimensional situation. Any questions, folks, with that main formula there? Okay, there's more words that go along with this, and they're worthwhile because we're going to expand this to a two-dimensional situation. So let's take a look at these bits and pieces right now while we're at it. Oh, sorry, they are. Where did I have that? Oh, it's right here. Sorry, got a little confused with my own notes. That's never a good sign. But here's the write-up for the summary of what we just derived. If we have more than 2 points, n different points, the whole derivation goes the exact same way, just a little bit more of a beast to get through. And this is what you get in the numerator. You get all the masses times all the coordinates on the x-axis, much like what we have right here. In your denominator, you get the total mass, like we have down here. These could be written more compactly as a summation of mass I times xi, summation of the total mass down below. And so here, that m is the total mass of the system in our denominator. The one I want to leave highlighted is this one. This one is called m, and it's referred to the moment of the system about the origin. It's the tendency for the system to rotate towards this direction or to rotate towards that direction. That numerator describes that tendency of rotation. So we just call it the moment about the origin. Well, any questions, folks, at the moment? Okay, so these are all the key formulas to get through a problem like this one. And here's just a really simple example to run through this. This is a legitimate homework question as well, and it could be a really short exam question since when you're dealing with centers of mass, it really is fundamental to start with 1 dimensions as a point mass system, 2 dimensions as a point mass system, and then start looking at a solid plate and finding the center of mass of that object. So if you're doing this one as a homework question or exam question, it might be a good idea to just draw this out. So here it goes. Here's our axis. We have masses 5, 4, and 8. They're located at -3 for x1, then x2 is at +1, so that's -2, -1, 0, 1, 2, 3, 4, 5, 6, 7 is our last location with a point mass.
Can it be 8?
Oh, 8 for, oh, that would be the actual mass itself. So right above on this, we'll say mass 8 in that location. So this one will be our x3. But good call, once we put this on, what we're kind of imagining is that the x-axis is really not a full x-axis. That's a rigid system connected by these point masses. Point masses is just to say that the rod is of so negligible mass, we're not even going to consider it in our computation whatsoever. Instead, we're going to put these in, point mass 5, 4, and 8, located at those corresponding locations. So we'll say 5 is mass 1, 4 is mass 2, and 8 is mass 3. So imagining this is maybe like 5 kilograms, 4 kilograms, 8 kilograms, what would you all say the system ought to balance? Any volunteers for a wild guess? Or this could be a fun way to do it. I'll move the red dot along the x-axis and just tell me to stop whenever it looks like we found where the fulcrum should be to balance the mass. On Zoom, you could just throw out a chat or just holler stop, and that'd be just fine as well. There could be a little bit of lag, but we'll do the best we can. Feel free to just say stop as well in class. So going from left to right, say stop or just type out stop the moment you decide that's where the fulcrum should be. Okay, looks like right about here. So let's put here, this is the location of X bar. Once I get everything working here. So it looks like people are pointing to right about here is X bar. I'll put a question mark there because we have to double check that and see if it's really true. Well, this is the formula for X bar broken down into computations. The numerator is M. N is going to be the summation of the point masses times the values of X. So it's going to be, just following the color coding, 5 times -3 plus 4 times 1 plus 8 times 7. So that's -15 plus 4 plus 56. So that's 60 minus 15 for a 45. So that's the tendency of the system to rotate about the origin. Next, we calculate M, the total mass. That's just taking summation of the point masses given in this problem. So 5 plus 4 plus 8. So that's going to be 12 plus 5, so 17. Finally, we're ready for X bar. X bar is M, the moment of the system about the origin, divided by lowercase m, total mass. M in this problem was 45. Lowercase m is 17. Might as well convey the color coding there. Looks like we want a calculator, but this is, oh, looking already pretty close to what everyone in the class is indicating should be the center of mass. So 45 divided by 17 gives us a 2.65. In this section, feel free to round to whatever seems numerically appropriate given the context for the problem. So 2.65. Where did we guess? This is 1, 2, 3. You know what? We are extremely close, and that's just where I decided people said to stop. You might have decided it was really out here. So our guess is close. It should have been right here. So that's calculating center of mass if you're dealing with a point system in one dimension. What we'll do next class on Thursday is scale this up to do 2 dimensions. We'll have the moment of the system about the x-axis and the y-axis. So m turns into mx and y. Denominator m stays the same, and the formulas are actually pretty remarkably similar. Then we'll scale that even up further and find the moment center of mass of a flat plate with uniform density. Our author calls it a lamina. But just think of a region, maybe a region like this, and imagine where would you put a fulcrum below to cause it to balance. So that's where the notes are going, and I think it's, again, a little bit easier than the presentation of hydrostatic force. So there's a little bit more homework questions in this direction, and these are more likely to be the actual real exam questions. Well, any last questions or comments, folks, before we call it a night? Okay, well, I appreciate everyone's patience. This was my first time doing hydrostatic force. It's a really rough read. Sorry about that going through it, but it's not going to be a major part of the class. Have a great night, folks. And when we come back, we'll finish off the rest of these formulas.
Thank you.
Yep, absolutely. Have a good one. Sure.
So I got the same thing as you, as the 1/2 y plus that
Oh, cool.
squared. And so then you get that.
I like the presentation here. So power 1/2, power negative 1/2. So we have, this turns into 3/2. So 2/3 times this would give us, yeah, a third there. This one becomes power 1/2. You had a 1/2 here. So yeah, that cancels out. Then 9 to power 3/2. 3 to 9 is 3 times power 3. That'd be a 27 right there.
Mhm.
Divide by 3 means it's back to a 9. So, oh, that's what you're doing right here. So a third, that turns into, well, let me take a look at that. So 9 power 3/2 would be root 9 cubed. So 3 cubed for a 27. So there it would have been a 1/3 times 27 for a value of 9 is what you should be getting for that part right there. Does that make sense for?
Aren't you taking the square root of 3/2 though, not just 3? Oh, you did that?
Yeah, I've got the root right there for the halves. Yeah. I think that's possibly where the numbers started to differ.
So right here just needs to equal 9.
Yeah, I believe that part turns into a 9. Let me double check. What problem number was that one?
19. Cause I always thought you took 9 cubed, then square root it. Or do you take the square root first, then cube it?
Actually, it's symmetric. You could do it in either direction, which is kind of cool.
But if you take the cube, if you take squared, oh, I said cube. I was like, if you take squared root of 27, you get 9.
Irrational now, yeah.
Thank you.
Yep, absolutely.